Now let us revise the crystal field theory. Crystal field theory, and we use a CFT as an abbreviation for crystal field theory. And this theory consider the ligand as point charges. Consider the ligand as point charges, and the attraction between the metal and the ligand purely electrostatic. And when the ligand comes into picture, or when the ligand starts approaching the metal atom, it produces a field around it. And in octahedral complexes, and most of the complexes of the D block elements are octahedral in shape. In octahedral complexes, the ligands approach the metal atom. The metal atom along the coordinate axis. Like plus x, minus x, plus y, minus y, and plus z and minus z. And the metal is at the center. And the 5 degenerate means having the same energy. 5 degenerate diatomic orbitals splits into 2 sets when the metal comes into contact with the ligand. When metal comes into contact with the ligands, and this is called d orbitals splitting. Now this is splitting diagram. Now these are the 5 degenerate diatomic orbitals in the absence of ligands. Now these are the 5 degenerate diatomic orbitals. 5 degenerate atomic orbitals in isolated gaseous metal atom, and they get excited when the ligand starts approaching the metal atom, but still they are degenerate. Now this is called the excited state, and finally this splits into 2 sets, a set containing 2 d atomic orbitals and the set containing 3 atomic orbitals. Now this set consists of dxy, dyz and dxz. These 3 orbitals have lobes along the axis, so they split more. Now dxy, dyz, dxz, now these 3 orbitals have lobes between the axes, so they're away from the direction of the ligands, and these 3 together are called the T2G orbitals. Now these 2 are dx2, y2 and the dz2. They have lobes along the axis, so they are repelled more strongly by the ligands, and these 2 are together called EG orbitals. And the energy difference between these 2, T2G and EG, this is called delta O. Now this delta O stands for the crystal field splitting energy in octahedral complexes or in octahedral field. Octahedral, a ligand field. And this delta O is equal to Hc by lambda. This is Planck's equation. Now the value of the delta O depends on mainly two factors, and the one is the nature of the ligand. So more the delta O, more the strength of the ligand, and more the delta O, lower the value of the lambda, wavelength. And on the basis of the magnitude of delta O, ligands can be classified as weak ligands. They have low delta O value, and second are strong ligands, and they gives a very high value of the delta. Now we take these two examples now. One is a complex of manganese with chlorine, MnCl6 3 negative, and the second is MnCn whole 6 3 negative. And both the cases the manganese is in the +3 oxidation state with the configuration of argon 3d4. And in this case MnCn whole 6 3 negative, also Mn is in the +3 with a configuration of argon 3d4. Now in this case these are the Eg orbitals and these are the T2G orbitals, and this is the energy increasing in this order. Same thing is here in the second complex. This is Eg set, this is T2G set, and the energy is increasing in this order. Now manganese 3 plus has 4 electrons. Now this is case number 1. First electron is in the T2G, second is in the T2G, third is also in the T2G, so we are following the Ohm's rule. Now in this case the delta O is very small in comparison to P, where P stands for the pairing energy required to pair up the electrons in the same orbital, pairing energy. Now since the delta O is very small in comparison to P, so it is easier to promote the electron to Eg orbital. So the fourth electron is in the Eg orbital, so all 4 electrons are unpaired. Now in this case the ligand is called a weak field ligand, since delta O is very small in comparison to the pairing energy. So more number of electrons remains unpaired. As a result, the complex is called a high spin complex. So we'll show higher value of the magnetic moment. Now on the other side, when manganese is in contact with the cyanide, the delta O is very large in comparison to P, so it's very difficult to promote electron to the Eg orbital. As a result, the pairing of electron takes place in the T2G. Now when the delta O is very large in comparison to P, the ligand is called a strong field ligand. Now as a result, we have less number of unpaired electrons. So the complex is called a low spin complex. So whether the pairing will take place or not, it depends on the strength of the ligand. It depends on the value of the delta O in comparison to the pairing energy. And the color of the complex is due to the excitation of electron from T2G to EG orbital, and this is called a DD transition. Now, when we arrange the ligand or the series in which the ligands have been arranged in order of increasing delta value or increasing crystal field splitting energy is called spectrochemical series. Spectrochemical series, because as the delta changes, lambda changes and the color changes. Now, some of the ligands which are arranged in the spectrochemical series are these. CO is the strongest ligand, then comes the Cn negative, then comes water, then comes ammonia, then comes water, and then comes Cl. Now, this is the increasing delta value. Now, we take one example. Now, suppose these are the three complexes given of nickel, NiCN whole 6, 4 negative, NiCl6, 4 negative, and NiNH3 whole 6 and 2 positive. Now, the increasing order of lambda is this. Now, this produces the maximum, the highest delta value. So, we'll have the shortest wavelength, and this produces the lowest delta value. So, we'll have the highest wavelength. So, this is the order of increasing lambda. So, as the lambda changes, the color changes. So, this theory is very useful in explaining the color of the complexes. Now, another important point is that all chromium 3 plus complexes, chromium 3 plus has a configuration of argon 3d3. So, all 3 electrons remains in the T2G, all 3 electrons remains unpaired irrespective of the ligand present. So, all chromium 3 plus complexes are octahedral, D2sp3 hybridized, inner orbital complexes, and paramagnetic irrespective of the ligand present. So, in D3, no pairing of electron takes place whether the ligand is a strong field ligand or a weak field ligand, irrespective of the ligand present. The only difference comes in the value of delta, in the value of lambda, and the color. So, if you look at these 3 complexes of chromium, they have all characteristics same except the color. They have different colors. So, all these 3 complexes of chromium are octahedral, right? They have the same hybridization, they have the same value of the magnetic moment. The only difference is in the color. So, these 3 complexes have different colors. Now, the second factor on which the value of the delta depends, the value of the delta also depends on the charge to a size ratio of the metal atom. So in this case, we keep the ligand same, but we change the metal and the metal with a different charge to size ratio. Now these are the two examples. One is a complex of cobalt CONH3 whole 6 with a charge of 3 positive. Second is NiNH3 whole 6 with a charge of 2 positive. Now in this case, the cobalt 3 plus has a higher charge to size ratio or higher charge density. As a result, will have higher value of the delta and all 6 electrons in cobalt 3 plus, all 6 electrons in cobalt 3 plus occupy the T2G orbitals. Like this is the cobalt 3 plus Eg, and these are the T2G orbitals. Energy is increasing in this order. So all 6 electrons are occupying the T2G. So they all pair up. In this case, the delta O is very, very large in comparison to P. As a result, this complex is inner orbital. This complex is a low spin complex. And this complex is diamagnetic. Inner orbital means it has a hybridization of D2sp3. And the complex is octahedral in shape. Now, if you look at the nickel, in this case, the nickel 2 plus has a lower charge to size ratio, so will produce less delta value, and as a result, no pairing of electron takes place. So we have a normal configuration, and only 2 unpaired electrons are present in the Eg. As a result, in this case, delta O is very, very small in comparison to P. The complex is called outer orbital complex. Outer orbital, it is a sp3 a D2 hybridized. Second point, it is a high spin complex. Since we have 2 unpaired electrons, so the complex will show paramagnetism. So it's a paramagnetic complex attracted towards the magnetic field and is octahedral in shape. So this crystal field theory is basically deals with the types of ligands, weak field, strong field ligands, and also very useful in explaining the color of the complexes. So this is all about the crystal field theory.